in chapter 4.2, we're going to take a look at types of studies. So the two most common types of studies are observational studies and experiments. So an observational study is when you observe individuals and measure variables of interest but does not influence responses. So the most common type of observational study in the medical field is when they stick people in a room and behind a two-way mirror, they're just watching them and writing down what they see. So they're observing, they're watching. They're not influencing the results like an experiment. So an experiment imposes some treatment on individuals to measure their responses. So a lot of drug companies use experiments when they're doing a trial for a new drug. They will do an experiment. They will give some people the new drug and others not, and so that testing of that new drug is an experiment. So they're seeing if that new drug impacts whatever they're trying to study, whether it's a new diabetes medication, heart medication, whatever it is. So they're trying to change their responses by using this drug. So if you're trying to understand cause and effect, experiments are the only source of fully convincing data. So being able to distinguish between an observational study and an experiment is very important in statistics. So we're going to take a closer look at why observational studies aren't used best. So there are two main reasons why observational studies aren't the best. The first is a lurking variable. So a lurking variable is a variable not among the explanatory or response variables in a study, but may influence the response variable. So for example, if you stick kids in a room and you give them two choices between an apple and an orange, and you're just observing what fruit kids like best, but suppose a kid is allergic to apples, so he can't pick the apple, he has to pick the orange. So you find out that most kids like oranges. That kid being allergic to an apple is a lurking variable. It wasn't something you were looking at, but it influenced the response. Next is confounding. It is sometimes referred to as a confounding variable. It's when two variables are associated in such a way that their effects on a response variable cannot be distinguished from each other. So, for example, you're observing whether or not heart medication affects whether or not someone has a heart attack. And you look at women of all ages, and you find that it doesn't have an effect. But older women are more likely to have heart attacks than younger women. So was it the medication, or was it their age? So did the medication not having an impact on whether or not they had a heart attack have anything to do with it? Or was it just because they're older and they're more likely to have heart attacks anyway? So that's an example of a confounding variable. You don't know which one actually had more of an impact on whether or not older women had more heart attacks than younger women, because those two variables were so closely related. So an experiment that's well designed takes steps to avoid confounding. So they'll make sure that if they're testing a new medication, they won't test it on younger women and older women. They'll try to avoid that by testing it on people of the same age, to make sure that age is not a factor in the experiment. So next we're going to take a look at some of the language found in experiments. So the first is treatment, which we already talked about in the definition of experiment. So I've kind of talked to treatment about like it being a drug or something like that. So it's a specific condition applied to the individuals in an experiment. So a lot of examples you're going to hear me talk about are applied, like giving drugs or not, testing new drugs. Experiments are very popular in the medical field and testing out new drugs. There's a lot of different other treatments as well. The next is experimental units or subjects. So it's the smallest collection of individuals to which treatments are applied. Now, experimental units don't have to be humans, but when they are humans, they're just referred to as subjects. They can also be animals. They can, pretty much anything can be an experimental unit. We specifically use the term subjects when they're people, though. So in picking a sample, there are good ways and bad ways. And the best way to do it is by using something that's called a randomized comparative experiment. So basically it means by assigning people to a treatment by chance. So treatments are assigned to all experimental subjects by chance. It's random. You don't pick and choose who gets to try the actual drug and who gets the placebo. So people may think that, so placebo is something that you give people so they're still taking a drug, but they don't know whether or not it's the actual drug or it's not. So kind of have a picture of what a randomized comparative experiment looks like. So you have your experimental units. You randomly assign them to 2 groups, 3 groups, how many groups you have, and then apply your 2 treatments. And then you compare the results. It's the best way to figure out if your experiment's good or not, if your results are accurate, is by doing random. Now, and even, so there's 3 principles of an experiment. First is controlling lurking variables that might affect your response. So using a comparative design is the best way to control for lurking variables. Random assignments, so not knowing who the people are, just randomly, it's impersonal. It helps get equal groups, balancing the effects of the lurking variables. And then replication. So you have to use enough experimental units in each group so that the differences can't be distinguished from chance differences between the groups. So you have to have a large amount of people. So you can't just use 10 people and split them into groups of 5. You may want to use 1,000 people and split them into groups of 500. So one of the common ways to perform an experiment is a double blind. So it's when the subjects and those who interact with them, they don't know if they're getting which treatment they're getting. So neither subjects nor those who interact with them and measure the response variable know which treatment a subject received. So double blinds are very common to make sure that the person who's doing the experiment doesn't unnecessarily influence the results. If they know who's getting the drug, they may skew the results, and then it shows it better in a better light than it actually is. So double blinds are very common. The next is something we call statistically significant. So what that means is that an observed effect is so large that it would rarely occur by chance. So next we're going to take a look at a couple examples to see if we can pick out a scenario, whether a scenario is an experiment or if it's observational. So our first example is a clinical trial is set up to compare a proposed new drug with a placebo, so some inert substance that is given to make people think they are taking a drug when they are not. 50 patients are recruited, and we randomly select 25 of them to receive the new drug. The rest receive the placebo. After some period of time, the 2 groups are compared to see whether the group receiving the new drug has recovered from the disease under study. So this is a common example of an experiment. So some of the common words in here that you want to pick out. So you're comparing a new drug with a placebo. So those are two different treatments. So some of them are receiving a new drug, some of them are receiving a placebo. So those are examples of treatments. It's a big red light that what you're looking at as an experiment. Our next example says, in an attempt to study the health effects of air pollution, a group of researchers selected 6 cities in different environments, some from an urban setting, some from a heavy industrial setting, and some from a rural setting. Altogether, they selected 8,000 subjects from the 6 cities and followed their health for the next 20 years. At this time, their health prognoses were compared with measurements of air pollution in the 6 cities. So this is an example of an observational study. So they're not imposing air pollution. It's not like they're exposing people to air pollution that wasn't already there. They're just looking at 6 cities. So they selected 6 cities and they followed their health. So they didn't actually do anything to these people. They were just watching them for 20 years. They weren't imposing anything on them. They didn't ask them to move to a city that had air pollution. So this is an example of an observational study. So next we have an example that says people who eat lots of fruits and vegetables have lower rates of colon cancer than those who eat little of these foods. Fruits and veggies are rich in antioxidants such as vitamins A, C, and E. Will taking antioxidants prevent colon cancer? A clinical trial studied this question with 864 people who were at risk for colon cancer. The subjects were divided into 4 groups: daily beta-carotene, daily vitamins C and E, all 3 every day, and daily placebo. After 4 years, the researchers were surprised to find no significant difference in colon cancer among the groups. So we want to know, what are the explanatory and response variables? So the explanatory, so what's going to influence our results are the vitamins, so taking the vitamins. The response is whether or not you have colon cancer. So if we're going to outline the design of our experiment, we start off with our 864 people. Okay. They're then randomly divided into 4 groups. So we have group 1, group 2, group 3, and group 4. Group 1 gets the beta-carotene. Group 2 gets vitamins C and E. Group 3 gets all 3. And group 4 gets a placebo. And at the end of the 4 years, you have your results. So when we talk about outlining the design of an experiment, this is what we're talking about. What you start with, how you're splitting them up, what each of those groups receive, and then finally taking a look at the results. So when we talk about no significant difference here in the outcome of the study, what does it mean? So in this case, it means the vitamins had no effect on whether someone got colon cancer or not. So not any one vitamin was a bigger deterrent to getting colon cancer than any of the others. So found that antioxidants didn't really have as much of an effect as they thought. Lastly, we want to look at some lurking variables that could explain the result. So why didn't the vitamins necessarily have more of an impact than we thought? And any variable you come up with that is related to a healthier lifestyle. So not only did some people maybe have those antioxidants, maybe they ate even more healthy things that meant they didn't get colon cancer. Maybe someone had all of those vitamins but didn't eat healthy and they still got it. So things that have an impact on your lifestyle are more likely to be a reason why there was no significant difference. Next we have that next we want to talk about a block design. So it's just another way to perform an experiment. So a block design is when a group of experimental units are known to be similar in some way that is expected to affect the response of the treatments. So what that means is, the best way to kind of explain a block design is through an example. So we have participants for the ACME medical study are assigned to blocks based on gender. So gender is a very common block design. Age is a common block design. So some similarity that could affect the response. So within each block, participants are randomly assigned to treatments, and for this design, 250 men get the placebo, 250 men get the vaccine, 250 women get the placebo, and 250 women get the vaccine. So we're talking about what this would look like. We have our 1,000 subjects that we started with all right? We then split them into men and women. Then within each of these, we have 250 with the placebo and 250 with the vaccine in each of the men and women. And then we would compare the results like normal at the end. So you think that there's going to be some difference between the placebo and the vaccine within the gender, so that's why you would do a block design. Another way to perform an experiment is by matched pairs. So this is a common form of blocking for comparing two treatments. And again, the best way to explain this definition is through an example. So in that same example from before, our ACME study, we have our 1,000 participants. And this time they're grouped into 500 matched pairs. So we have two things we're going to look at. So gender and age. So we're looking at a pair that's two women both 21, or a pair that's two women, both 22. And then we would keep going with ages and gender. So this design, designs like a matched pair control potential lurking variables, age and gender, whereas a block design looked at just one potential lurking variable, gender. So if you know there's multiple potential lurking variables, that's where matched pairs come into play. Or if there's just one you're taking a look at, that's where a block design would come into play. I'm not going to draw out the design for the matched pair because I'm not going to draw out 500 groups. But if you have any questions over anything from this section, please let me know.